In matrices, if you remember, if I'm adding two matrices to each other, it's very, very simple. I'm adding the corresponding elements. But in determinants, if I need to add two determinants, if this determinant is 1, 2, 1, 3, for example, 2, 4, and 1, 0, 0, and 2, if I want to add it on another, determinant, it has to have two rows exactly the same. So in order to be able to do the addition process, the first row must be, for example, the same. The last row must be exactly the same. I can change the values in the second row, and the result will be, the first row will be the same, the last row will be the same. The addition process will happen with the second row only, so it's going to be a 4, then a 5, then a 1, like this, which is completely different than matrices. Matrices, you add the corresponding elements, A11 plus A11 give you A11U, and so on. شباب انتوا فاهمين بقول ايه؟ القصه دي غايه في الاهميه. في الماتريسيز مصفوفات تجمع كل الارقام، كل واحد قدام اخوه، لازم يبقوا لهم نفس الدايمنشن. بس in determinants اولا عشان ينفع the condition for addition, they will have to, the change just will be in one row. That's the row that will be added from these two matrices. يعني لازم الصفوف كلها تبقى زي بعضها، ومين بس اللي متغير وانت بتجمع؟ صف واحد او عمود واحد. This is very important. Okay, once more, annulment, which means a matrix two identical rows, the value will equal to 0. So if you have a determinant and it has two identical rows, or maybe identical by taking a constant, okay, so the value of this determinant will equal to 0 directly. If you have a complete row, it will equal to 0. The determinant of the identity matrix is 1. So the determinant of the elementary matrices is 1. Answer me. If the determinant of the identity matrix is 1, if the determinant of the elementary matrices is 1, is it correct? Think. Why it's not? But when it's going to be correct? It's going to be correct only if you multiply a row by a number and adding it into another row, because this is not going to change the value of a determinant. So the elementary matrix, okay, with multiplying row by a number and adding it on another row, the value of the elementary matrix will equal to 1. But the other two operations, Mr. Hussein, in elementary matrices will have different values than 1. So if you replace rows, for example, the value of the determinant is going to equal to -1. If you multiply a row by a number, then the value of the determinant of the elementary matrix will be that number that you multiplied with. انتوا معايا يا شباب؟ فاهمين كويس اللي انا بقول لك عليه؟ ده مهم جدا. Okay, these are the main operations, as I told you. The value of determinant changes. The value of determinant changes sign if two rows are interchanged. Multiply by a row, a non-zero constant corresponds to multiply the determinant by this value. Adding a row to a constant multiple in another, it's not going to change the value of the determinant. This is what I was telling you about. Okay, determinant of the elementary matrices. In specific, if you multiply by alpha, the alpha will appear. If you change, the sign will change. If you add to a row a multiple of another row, the value is not going to be changed. Okay, I want you to remember these are the ones that I was telling you about. This is the replacement. The value of the determinant is going to be negative. Multiplying by alpha is going to equal to alpha. If you multiply to a row a multiple of another row, the value will remain the same of an identity matrix. Of course, determinant E times A, elementary matrix times any matrix, يساوي determinant of A times determinant of A. Satisfy the following determinants of a triangular matrix. The determinant of a triangular matrix is the product of the diagonal elements only. A matrix is A is invertible if and only if its determinant doesn't equal to 0. And in this case, this matrix is called non-singular matrix. So any matrix with a determinant doesn't equal to 0, it's called a non-singular matrix. For any n by n matrices, the determinant of A and B is equal to determinant of A times determinant of B. You may need this property down the road. Remember that determinant A minus 1, it's 1 over determinant of A, which is important. Also, determinant of A transpose is equal to determinant of A. Those properties are important. Okay, of course, one of the major properties, and you've been asked about this more than once, how to get an inverse of a matrix. Do you remember the steps of getting an inverse of a matrix? We have how many types or how many methods? 2 methods. Either writing the matrix and the identity matrix in front of it, and trying to get a reduced echelon form, you will get your inverse. Am I right? The other method is the cofactor method or the adjoint matrix method, which means you will stop at each element, eliminating its row and its column and getting the smaller matrix. Okay, determinant with the sign, and those are called cofactors. Once you do a transpose for the cofactors, you will get the adjoint matrix. And of course, you know that A minus 1 is equal to 1 over determinant of A times the adjoint matrix. This is really very important. This is a very important property. Look at it carefully. That the A minus 1 is equal to the adjoint matrix divided by the value of a determinant. So this is how to prove this problem or how to solve this problem. I need an idea. How to solve it? How to get the right answer? He's giving you A, B, and C, B invertible matrices of size n by n. The expression A, then I plus C, A minus 1, B minus blah, 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 is equal whatever. And it is necessarily equal to which option? So I need to do simplification to discover it. How to go through it. This is why I did go through the proof with you. Okay, do you remember the proof that I told you about, the uniqueness of the inverse matrix? It's going to be with the same steps. Any ideas, Mr. Roman? How to solve this problem? It's going to be really very simple. All I need to do in order to simplify all of this is to start with removing from any side the matrices that already exist. So all I have to do, since he just gave me one piece of information, that A, B, and C, all of them are what? What's the invertible matrices? That you can get its inverse. So I can start by multiplying this row, all of it, by A minus 1. So let's multiply by A minus 1. If I multiply by A minus 1, and please, once you multiply, respect the direction of multiplication. So I will multiply from the left. So it's going to be A minus 1 times A. This is I, my plus a C of an A minus 1, and all of them multiplied in B. I will talk about this part only. The rest will be the same. But if you try to multiply by A minus 1, what's going to happen, Mr. Omar? A minus 1 times A will remove this part. So you will have I, that's plus A minus 1 times C times A minus 1 times B. So multiplying just only by A minus 1 already. A minus 1 times A, it will disappear. But A minus 1, okay, yes, it will disappear. So it's not going to appear here, I'm sorry. It's not going to be appearing here. So multiplying by A minus 1 from the left side, it's going to remove A. So all you will have A, I, plus C times A minus 1 times B. Then if I want to remove B from this side, all I have to do is to multiply by B minus 1, but from the right. If I did so, you will have B minus 1 times B, and it will remove each other, so you will end up having I equal to C, A minus 1. And once more, I will do the same with each part of them. But of course, I will respect the signs. which means if I multiply it by a minus 1, this guy will be multiplied by a minus 1, this one will be multiplied from the left by a minus 1, and this one too will be multiplied. Hussein, can you simplify this part for me?
AB.
Huh? AB? ايه؟ BA قصدك. صح؟ It's going to be BA. Why? Because transposition will make A transpose over transpose, but multiplied by B transpose over transpose. So actually, this part is simply B times A. Are you with me? Are you with me? This is mainly depend on the propositions that we spoke about. If you try to multiply, do the same, this is going to be the right answer. Also for a problem like this, which is mainly about the dimension of multiplication. How to solve this, Juman, it's really very simple. He is asking you, let A and B be matrices such that B has how many rows? 3 rows. And the AB, the result of multiplication is 4 by 2. So he will ask you about the dimension of A, which is an accessible question for you. Can you think about it? How to do it? I will go through the conditions. I will do it for Jumana. Okay? This problem is really very simple. All I have to do is asking me that A times B, and we already solved it previously, A times B together, the dimension is 4 by 2. And this is going to happen if you multiply the matrix A by matrix B. All you know is that matrix B has just only 3 rows. So, since matrix A has 3 rows and there is a multiplication, then matrix A must have 3 columns from the probabilities of multiplication. And once more, look to the dimension of the result, which is mainly it's going to be times 2 and this is times 4. So actually these 2 matrices with the columns of the first matrix equal to the rows of the second matrix, that's condition of multiplication, and the result will be the 2 numbers outside, which is 4 by 2. So the correct dimension for A is going to be 4 by 3. So I think this guy is correct. This is also an example of how to do multiplication. So it's actually 4 over 4 times 3. Any questions? Okay, that's it for this lecture, which is an overview about our course or about the previous parts that will be involved. If you have, we may have a small question about vector spaces. It's going to be about the generation or the proof of vector space, so just review it. Tomorrow, I will try to solve with you in another revision lecture of tomorrow, a system of equations which with having unknowns like alpha and beta, and we are classifying this system, and we will see also a couple of problems about the determinants or something like this. So thank you very much. Please try, if you have time, to go through all of this in order to be able to solve with me tomorrow. Thank you very much. I'll see you next time. Thank you.